To navigate to the Infinity app, put the Maths app URL in your browser address bar, click on Pure, and then on the menu will be a link to the button for Introduction to Infinity. The alternative way is to go via the topic maps here, and there will be a button to Infinity up here, and either from the topic map you can select a particular topic, or from the alphabetical list here. So if we click Limits Apply to Functions, we can see the prerequisite topics and the follow-on topic in this app, and then in the sidebar will be a link to that particular topic within the app. So let's go to the introduction and think about what inspires this particular application. And when I came across calculus for the first time, the word limit appeared quite quickly, and when I read about it, I very quickly got bogged down in the ideas and techniques behind limits, and I decided to leave that alone and just learn the techniques of differential and integral calculus. In this app, I'm going to introduce some of the ideas of infinity to act as a stepping stone from calculus to a much more formal and rigorous technique of real analysis to understand the foundations of calculus. But also the idea of infinity can be used before we get to university level, so we have some idea of what we mean by a process being infinite, or what we mean by infinity. Now, an inspiration to this particular app is an excellent book by Stephen Strogatz, and the book is titled Infinite Powers. The book contains far more detail, both technical and historical, but even though it's technical, it's very approachable. It's not intimidating like a regular university maths textbook on infinity or real analysis. If you're at all interested in this subject, I would definitely recommend you get a copy of that book. I don't get anything from recommending it. I'm just saying I would say go there as a source of really useful information, and it gives you a much deeper and broader understanding of this topic, which then becomes important for a whole range of later mathematical topics. The other book I would definitely recommend is A Very Short Introduction to Mathematics by Tim Gowers, and although it's not specifically about the infinite, it does give you a very useful introduction to the idea of proof, and a particular section about a limit being a competition, and the ideas how to think about the epsilon delta relationship in a limit. This first video will talk about the foundational ideas and how we first come across the idea and the word infinity. Our first encounter is almost always the idea of the number line, where we have integers or counting numbers. And quite quickly we become aware that we can keep on adding 1 to any whole number, any integer, and get another number which is bigger, and then add another one and another one. Everybody, I would say, gets caught by this idea and this challenge that the numbers never end. So in this app, you can animate that by saying, let's start counting by adding 1. And you can see that it will never end. So we introduce ideas of, and words and terminology about, items or objects being mathematically finite. And we're familiar with that we can count how many things there are. by using the counting numbers. So simply the positive whole numbers up to 6 starting at 1, we can write using the curly bracket set notation as 1, 2, 3, 4, 5, 6. Or if we're not using whole numbers, but we start measuring items like the weight of a particular vehicle, we can say to a certain degree of accuracy what the weight of a vehicle is. So its weight is finite. We can assign a number to it. So items that can be measured or counted and have some number associated with them are finite. So then, in contrast to that, any object for which we cannot count or measure some property of it, then we can say that there is an infinite quantity associated with that item. So what we're trying to understand, discover and explore, are there any processes that never stop, such as adding a number, that can be associated with an infinite number of steps that can somehow result in a number or value or answer that is itself finite? And that seems a contradiction. How can we have an infinite process, we keep on doing a particular action, and that somehow the answer will be infinite? Down here, we've got some questions that you should think about and answer in your head before clicking on them and seeing what the app says is the answer, such as, what's the largest integer? Is infinity a number? And are there different sizes of infinity? Now, some of them you might have to guess what the answer is, but that's okay, even if you get the wrong answer, because you're starting to think about infinity and some of the problems and contradictions associated with that. So beyond the number line, we start coming across basic numbers. Have a look at the number systems section of the Proof app for a bit more detail of the different types of numbers and how they're related to each other. We can think that there are whole numbers, such as positive, negative, and 0. Then generally we get introduced to fractions, also known as rational numbers. And then quite a bit later, the shadowy idea of irrational numbers. Numbers which we believe are on the number line, but we can't accurately express using fractions of integers. And the famous ones are √2, pi, and e. And in this app, we'll assume that you know what a whole number is and how to divide whole numbers to make fractions. What about the problem of identifying infinity as a number? Think about how we calculate using decimals and integers. And then think about what would happen if we created a symbol, this number 8 on its side, which we call infinity, and started doing some calculations with that. And we find quite quickly that we run into problems and contradictions. And then down here, after reading through that, think about and try and come up with an answer. Why does infinity times 0 lead to a contradiction? And is it always what we call indeterminate? And the third area in the introduction are early encounters with infinity, when we try and do calculations of an infinite sequence of actions. And when I say infinite here, I mean we just keep on doing the same calculation again and again and again without end. I'll say without end rather than without limit. Okay. Let's think about adding numbers together. And the simplest sum of numbers or series is the sum of the positive whole numbers or the positive integers. And if we study this and we have a finite number of positive integers starting at 1 up to n, and we add all of them, we can show, or we are told, that the result or the sum is n times n plus 1 over 2. And then if you click on the different buttons, you'll find that there are other sums that we can think of. Okay, now there's a fixed number or a finite number of terms. Okay, and if we take the triangular numbers, or the sum of the positive whole numbers, and then keep on adding, and then have a look at what the total or the sum looks like, you can see that that sum is increasing without end. So as we add more and more numbers, the result increases. So that's not going to come to a finite answer. And we can see what the result is when we add 20 terms. A geometric sum is when we add terms where each successive term is the previous number multiplied by some other number. And the simplest one is usually 1 plus a half plus a quarter plus an eighth, where we're multiplying each number in the sequence within the series by a half each time. Now the question is, what happens when we add those numbers together? So the first value is 1. We're going to add a half and we get 1.5. We add a quarter, we get 1.75. We add an eighth and we get 1.875. If we go to, say, the sum of the first 20 terms, we've got 1.999999809, and this is getting closer and closer to 2. And finally, we'll think about what happens when we add the reciprocals of the positive integers. 1 plus 2 plus a third plus a quarter plus 1 over 5 plus 1 over 6. And the individual terms are getting smaller, but we can show that the sum never reaches a finite number. Looking at that, what we call the harmonic sum, and let's take, say, 5 terms, we get 2.283, and then we take 40 terms, we get 4.2785. We take 98 terms, we sum them together, we get 5.1673. And it turns out that as we add more and more terms, the sum increases incredibly slowly, but eventually will become bigger than any number. So this sum is divergent. Similarly, if we add the reciprocals of odd numbers, 1 plus a third plus a fifth plus a seventh, even though we've got fewer terms, the sum is still increasing more slowly, but it turns out that this also diverges. The questions are, why does the harmonic series diverge if 1 over n is getting closer to 0? And does the odd harmonic series, 1 plus a third plus a fifth plus a seventh, diverge for the same reason as the divergence of the basic harmonic series? And finally, there's a discussion of how we can use infinite series, infinite sums, to calculate the area of a circle by dividing it into more and more slices or sectors. And the explanation for the formula of the area of a circle is given here.